All right, subscribe to the channel and hit the bell. I'm Dragon Megalodon, and you are locked into What Did the Code Say? Your ultimate explainer breaking down the pure math driving your favorite systems. Today, we are opening up the Coordinate Geometry Developers Toolkit. We're going to translate some raw theoretical math into the exact executable logic you need to completely master 2D space. Let's just boot this up and dive in.
So, here is the big question, right? How exactly do you calculate distance without just completely crashing your logic? I mean, think about it for a second. Whether you are spawning a loot crate, tracking an enemy's line of sight, or building a hitbox, you absolutely have to understand the space between objects. We're going to hook into these math concepts by treating them as your foundational code. This is the stuff you need to execute essential mechanics like collision detection and object spawning.
All right, level 1, decoding the distance formula.
Now, before we can even think about building complex interactive environments, we need a rock-solid way to find the exact linear distance between two sprites. That's where the distance formula comes in. It's basically the square root of the quantity x2 minus x1 squared plus the quantity y2 minus y1 squared. This script takes your first coordinate point, x1, y1, and your second point, x2, y2, and outputs the precise length between them. And honestly, here is the brilliant feature of this algorithm. It literally doesn't matter which point you assign as point 1 or point 2. Why? Because we are squaring the differences. Any negative values instantly get converted to positives before they're even added together.
But I see developers throw syntax errors on this all the time. A super common beginner bug is mixing up where the plus and minus signs actually go inside this formula. So let's debug this right now. This formula, it isn't magic. It is literally just the Pythagorean theorem in a disguise. Remember good old a squared plus b squared equals c squared? Yeah, if you draw a right triangle between your 2 points, the difference in the x-coordinates is side A, the difference in the y-coordinates is side B, and that distance between them is your hypotenuse C. So we find the difference between coordinates with a minus, and then we add those squared lengths together with a plus. Boom, simple as that.
Okay, let's compile this with some real data so you can see it in action. We'll execute the formula using two coordinates, -1, 5, and 4, 2. First up, we find the difference in our x's. So 4 minus -1, which actually flips to 4 plus 1, right? Giving us 5. We square that to get 25. Next, the y's. 2 minus 5 gives us -3. Square that guy, and we get a positive 9. Add 25 and 9 together, and this perfectly compiles into a final distance output of the square root of 34. Clean, precise, and completely bug-free.
Moving on to level 2, finding the exact midpoint. Look, knowing the distance is great and all, but what if you need to know the exact halfway spawn point between two coordinates? Enter the midpoint formula. And notice something here. We aren't dealing with a crazy, complex physics calculation. I want you to decode this formula as just a simple averaging algorithm. Literally, to find the exact center of a line segment, you just calculate the average of your x-coordinates and the average of your y-coordinates. Add them up, divide by 2. That is the entire script.
Let's run those exact same coordinates through this midpoint algorithm. We take point 1 at -1, 5, and point 2 at 4, 2. The average of our x-coordinates is -1 plus 4 divided by 2, which gives us 3 over 2. The average of our y-coordinates is 5 plus 2 divided by 2, which gives us 7 over 2. Just like that, the algorithm immediately outputs the precise halfway coordinates of 3 halves and 7 halves.
All right, level 3, programming 2D hitboxes. So linear math is solved, but games aren't just straight lines, right? We need to define circular areas. Think like a blast radius or a zone of control. Now the standard form of a circle is x minus h squared plus y minus k squared equals r squared. In this particular syntax, r is our radius, and h and k represent the x and y coordinates of our center point. Notice how similar this looks to our previous code. If you square both sides of our trusty distance formula to get rid of that square root, it literally generates this standard general equation for any circle. Any point xy on this circle will always have a distance of exactly r from the center hk.
Let's actually walk through building a circle's equation from scratch. Say our target radius is 6, and our target center is sitting at 0, -3. We drop these right into our syntax. X minus 0 squared plus y minus -3 squared equals 6 squared. Now notice how subtracting a -3 cleanly flips the sign to a +3. So our compiled simplified equation becomes x squared plus y plus 3 squared equals 36. Okay, now let's reverse engineer one. What if the engine hands you the compiled code and you need to parse out the parameters? Let's say we have the equation x minus 5 squared plus y plus 6 squared equals 5. Because the standard format relies on subtracting the center points, an x minus 5 actually means our x center is a positive 5. A y plus 6 means our y center is a negative 6. And since the right side is always r squared, our radius is simply the square root of 5. Bam! We just extracted the core data directly from the structure itself.
We made it! Boss level. Decompiling hidden circle equations.
All right, buckle up, because we have officially reached the ultimate developer challenge. Sometimes you just aren't given clean code. Take a look at this absolute block of mathematical spaghetti code. 9x squared plus 9y squared plus 72x minus 18y plus 36 equals 0. Yikes, right? This does not look like a circle. The parameters are completely buried. But don't worry, we're going to fix this using a legendary refactoring trick called completing the square.
Let's break down the initial formatting steps. First things first, we need to clear out the garbage coefficients attached to our squared variables. So we divide everything by 9. That cleans it up nicely to x squared plus y squared plus 8x minus 2y plus 4 equals 0. Much better. Step 2, we group our families together. Put the x terms side by side, x squared plus 8x. Put the y terms together, y squared minus 2y. Finally, step 3, just subtract that constant number 4 right over to the right side of the equal sign. Okay, so now our equation is organized, but we still have an open circuit. Here is where we execute the core completing the square algorithm. Focus on the coefficient attached to the plane x, which is 8. Cut it in half to get 4, and then square it to get positive 16. Now, do the exact same thing to the plane y coefficient, which is negative 2. Cut it in half to get negative 1, square it to get positive 1. Now, step 3 is absolutely critical. To maintain the balance of our code, we must inject that 16 and that 1 into both sides of the equation. And check out how this trick magically works. By injecting those specific numbers, we can now compress the expanded terms into perfect standard form squares. The x squared plus 8x plus 16 perfectly wraps up into x plus 4 squared. The y squared minus 2y plus 1 perfectly wraps up into y minus 1 squared. And on the right side of the equal sign, our constant of negative 4 plus the 16 and the 1 we just added cleanly sums up to 13.
Let's reveal the beautifully decompiled final code. Our refactored equation is x plus 4 squared plus y minus 1 squared equals 13. Just like that, the hidden data is totally exposed. We can effortlessly read off our decoded center as negative 4, positive 1, and our decoded radius as the square root of 13. We literally just turned complete spaghetti code into a perfectly functional 2D hitbox.
Now, if you're wondering why this algorithm is so bulletproof, here's a really brief proof for you. When you expand a standard square, like x minus h squared, it multiplies out to x squared minus 2hx plus h squared. Our trick of taking half of that middle coefficient, half of negative 2h is just negative h, and then squaring it, perfectly and reliably generates the exact h squared we need to wrap the whole string back up into a tight, secure parentheses. It works every single time. So what is the takeaway from this explainer? Distance calculations are really just the Pythagorean theorem in disguise, and completing the square is your ultimate refactoring tool to reveal hidden collision logic. Master these two things, and your spatial algorithms will never crash. If you want to understand what the code says before it explodes, hit subscribe. Also, please don't forget to like this explainer. This tells YouTube that technical content is still alive and thriving on the platform. And go ahead and share this explainer with a beginner coder who really needs help debugging their geometry logic. Keep building, keep optimizing. And you? What did the code say in your project today?